You see them in movies, harbingers of doom, city killers, extinction events, but Hollywood never tells you the full story. There are dirty snowballs drifting for thousands of years. There are shattered fragments diving into the sun at temperatures that melt steel. There are visitors from other stars, carrying ice older than Earth itself. Some take 75 years to return. Others appear once and vanish forever into the void. Which ones should terrify you? Which ones are already on their way? What happens when a comet the size of a city decides Earth is next? As of July 2025, we know of 4,584 comets. That number climbs every month. 123 are near-Earth comets. 74 belong to the Encke family. 815 are Jupiter family comets. 109 are Halley type, and 3 have arrived from beyond our solar system, carrying secrets from alien worlds. Each type follows different rules. Each type carries different dangers. And the classification that saves your life depends on orbital period, composition, trajectory, and one critical number, how close it gets to you. If you value documented astronomical history like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. Also, this script is researched and factual. Using sources from the Astrophysical Journal published in January 2025 on the demise of Kreutz sun-grazing comet C 2024 S1 Atlas, NASA's Center for Near-Earth Object Studies, current catalog data from December 2024, podcast, and the monthly notices of the Royal Astronomical Society from November 2021, analyzing the Oort cloud origins of long-period comets, sources that track every documented comet passage and impact probability calculation in the solar system. Now back to the information. Start with the simplest split, periodic versus non-periodic. Periodic comets orbit in under 200 years. Non-periodic comets take longer or never return at all. But that clean division hides brutal complexity. Periodic comets die young. Solar radiation strips them. Planetary gravity tears them. Each passage costs mass. Each pass brings them closer to extinction. Non-periodic comets arrive pristine from the darkness, packed with volatiles, unpredictable, often invisible until they're already close. The detection gap is the killer. We catalog periodic comets decades in advance. Non-periodic comets, sometimes months, sometimes weeks, sometimes not at all. Take Encke-type comets, orbital periods under 20 years. They never reach Jupiter's orbit. Comet Encke itself loops the Sun every 3.3 years. As of July 2025, 74 Encke types are known, 6 classified as near-Earth objects. These comets shed fast. Every orbit burns ice, exposes rock, dims their brightness. Comet Encke is dying. In a few thousand years, it will be an asteroid, indistinguishable from the rocky debris it once avoided. But while it lives, it sheds the torrid meteor stream, thousands of fragments that Earth passes through twice yearly. Some fragments measure meters across, big enough to punch through atmosphere, big enough to explode over cities like the Tunguska event in 1908, which flattened 2,000 square kilometers of Siberian forest. The torrid complex holds larger debris, too. Ground-based telescopes tracked objects up to 1 kilometer embedded in the stream. The stream crosses Earth's orbit twice. Southern torrids in October, northern torrids in November. Most years produce gentle meteor displays, 50 per hour maximum. But every few years, enhanced torrid showers occur, rates jump, fireballs multiply. In 1947, a torrid fireball exploded over the USSR. In 2015, enhanced activity produced dozens of bright meteors across multiple continents. Astronomers debate whether Comet Encke itself could have been captured from the Oort cloud thousands of years ago, gradually shortened its orbit through repeated Jupiter encounters, and is now in its death throes, or whether Encke represents primordial Kuiper belt material nudged inward. Either way, its corpse will haunt Earth's orbit for millennia. Jupiter family comets orbit in under 20 years with inclinations below 30 degrees. As of July 2025, 815 are cataloged. 153 cross Earth's orbit. These comets cluster near the ecliptic plane where planets live. Their aphelia match Jupiter's distance, 5.2 astronomical units. Jupiter's gravity shapes their paths, pulls them in, spits them back out. Some get captured into shorter orbits, some get ejected entirely. The dance is violent, and Jupiter, twice as massive as all other planets combined, controls the choreography. Comet 67P. Churyumov-Gerasimenko became famous when ESA's Rosetta mission orbited it from 2014 to 2016. Nucleus shaped like rubber duck, 2 lobes connected by narrow neck, 4 kilometers long. Mass 10 billion tons. Density 0.533 grams per cubic centimeter. Lighter than water. Porous like pumice. Surface temperature reached 200 degrees Celsius at perihelion. Water vapor, carbon dioxide, carbon monoxide, methane, ammonia, all detected streaming from active regions. Dust to gas ratio varied from 1:1 up to 4:1 depending on location and time. The mission revealed comets aren't dirty snowballs but snowy dirtballs, more dust than ice by volume. And the duck shape wasn't unique. Comet 103P Hartley 2, visited by NASA's Deep Impact Probe in 2010, and SEAS, showed similar dual lobe structure. Comet 8P Tuttle, observed by multiple spacecraft, displays irregular potato shape with distinct terrain units. These are contact binaries, two objects that merged gently at low velocity early in solar system history, then stuck together. Jupiter family comets fade faster than Halley types because shorter periods mean more solar passes. Comet 2, P, Encke lost 30 meters of surface material per orbit on average. Comet 67P loses 1 to 10 meters per orbit depending on activity level. After hundreds of orbits, the volatiles deplete, inactive crusts form. The comet goes dormant or dies completely. But not all Jupiter family comets behave. Comet 29P, Schwassmann. Bachmann 1 orbits every 14.9 years entirely between Jupiter and Saturn, never approaching the Sun closer than 5.7 astronomical units. Yet it exhibits massive outbursts. Brightness increases of 5 magnitudes in hours. Not solar heating. Subsurface ice pockets suddenly exposed by landslides or internal pressure release. The outbursts are unpredictable. Decades can pass between events, or multiple outbursts occur within months. Astronomers still don't fully understand the trigger mechanism. Halley-type comets orbit between 20 and 200 years. Inclinations range from 0 to over 90 degrees, random orientations that suggest deep space origins. As of July 2025, 109 Halley types are known. 36 cross Earth's orbit. Halley's comet itself returns every 75 to 76 years. Last seen in 1986, next arrival 2061. Its nucleus measures roughly 10 kilometers by 5. Its orbit reaches beyond Neptune at aphelion, 35 astronomical units. When it swings through the inner solar system, it's moving at 54 kilometers per second relative to Earth. That velocity is the threat multiplier. Halley types hit harder than Jupiter family comets because of speed. Energy scales with velocity squared. 54 kilometers per second delivers catastrophic kinetic energy. Historical records of Halley's comet extend back to 240 BCE. Chinese astronomers documented it in the Shijie Chronicles. Babylonian clay tablets may record earlier apparitions. The comet appeared in 66 CE, visible during the First Jewish-Roman War. In 987 CE, European chronicles describe it as fearfully bright. The Bayeux Tapestry depicts the 1066 apparition. William the Conqueror saw it as divine approval before invading England. Harold Godwinson saw it as omen of doom. Both were right, depending on perspective. In 1456, Pope Calixtus III allegedly excommunicated the comet as instrument of devil. That story is likely apocryphal, but reflects medieval terror of celestial portents. Edmund Halley calculated its orbit in 1705, recognized it appeared every 75 to 76 years, predicted the 1758 return, and died 16 years before vindication. When it returned as predicted, it became 1P Halley, the first numbered periodic comet. The 1986 apparition brought armada of spacecraft. ESA's Giotto probe passed within 600 kilometers of nucleus on March 14. Images revealed active jets on sunward side, dark crusty surface with albedo 0.04, blacker than coal. Soviet Vega probes flew past at 8,000 kilometers. Japanese Suisei and Sakigake missions observed from greater distances. NASA's International Cometary Explorer retargeted from Comet 21P Giacobini-Zinner. Collectively, these missions revealed nucleus dimensions 7 by 15 kilometers, rotation period 52 hours. Mass 3 times 10 to the 14th kilograms. Dust particles struck Giotto's shields at 70 kilometers per second, punching holes in protective layers, but spacecraft survived. One particle impact knocked the probe off axis. Interrupting transmission briefly, engineers regained control, the mission succeeded, and humanity got first close-up views of Halley's ancient, battered nucleus spinning through space. Long-period comets, orbital periods over 200 years. Some take thousands of years, some take millions. They originate in the Oort cloud, a spherical shell of trillions of icy bodies extending from 2,000 to 200,000 astronomical units from the Sun. The Oort cloud has never been directly observed. Its existence is inferred from comet orbits. Passing stars disturb the cloud, galactic tides disturb the cloud, giant molecular clouds disturb the cloud, and occasionally a comet gets nudged inward. When it arrives, it's moving fast and unpredictable. Jan Oort proposed the cloud's existence in 1950 after studying long-period comet orbits. He noticed aphelia clustered around 20,000 astronomical units. This suggested a spherical reservoir at that distance. Estonian astronomer Ernst Öpik had proposed a similar idea in 1932, but Oort provided mathematical framework and observational evidence. The cloud divides into two regions: inner Oort cloud or Hills cloud from 2,000 to 20,000 astronomical units, and outer Oort cloud from 20,000 to 200,000 astronomical units. Inner cloud is disc-shaped, aligned with solar ecliptic. Outer cloud is spherical, isotropic. Material in both regions formed closer to Sun, between Jupiter and Neptune during solar system formation, then got scattered outward by gravitational interactions with giant planets. Over millions of years, passing stars, galactic tides, and random encounters circularized the orbits, creating stable reservoir. The Sun orbits galactic center every 225 million years. During this orbit, it passes through spiral arms, crosses galactic midplane, encounters stellar density variations. Each passage perturbs Oort cloud. When Sun crosses galactic plane, gravitational gradient from disk material tugs on cloud's outer regions. Tidal forces dislodge comets. Impact rate on inner planets temporarily increases. Some researchers propose correlation between galactic plane crossings and mass extinction events on Earth, though evidence remains controversial. The periodicity would be roughly 30 million years, time between plane crossings, but asteroid impacts also spike during same periods, making causation difficult to untangle. Stellar encounters provide stronger perturbations. The Sun passes within 1 light year of another star roughly every million years. Close encounters within 0.5 light years occur every 10 million years. When a star passes through outer Oort cloud, gravitational disturbance sends hundreds or thousands of comets sunward. Cometary shower begins. Impact rates on Earth increase by factors of 10 to 100 for several 100,000 years. Then the shower ends. Cloud settles. Background rate resumes. The last major stellar encounter occurred roughly 3 million years ago. Schultz's star, red dwarf system that passed within 0.8 light years. Too distant to seriously perturb cloud. But in 70,000 years, Tycho's Gliese 710 will pass within 0.16 light years. 10,000 astronomical units. That's deep into outer Oort cloud. Hundreds of comets will get dislodged. Some will arrive in inner solar system between 1 and 2 million years from now. Future civilizations will face elevated impact risk unless they develop comprehensive detection and deflection infrastructure. Current detection technology spots long-period comets at roughly 5 astronomical units, less than 1 year warning for potential Earth impactors. The mean impact probability for a long-period comet crossing Earth's orbit is 2.2 to 2.5 times 10 to the negative 9th power per perihelion passage. The mean impact velocity is 52 kilometers per second. But the most probable impact energy corresponds to 56 to 58 kilometers per second. At those speeds, a comet nucleus large enough to create a 10-kilometer diameter crater strikes Earth between 5 times 10 to the negative 7th and 2.8 times 10 to the negative 6th times per year. Best estimate, 1 times 10 to the negative 6th per year. Nuclei large enough to trigger global climate catastrophe strike every 16 million years on average. But those are averages. Cometary showers change the math. When a major perturbation hits the Oort cloud, a close stellar passage, a molecular cloud encounter, thousands of comets get dislodged simultaneously. Impact rates spike. The last major shower may have occurred 65 million years ago. The Chicxulub impactor that ended the dinosaurs might have been a comet. The iridium layer, the global firestorms, the decade of impact winter, all consistent with a 10-kilometer comet arriving at cosmic velocity. Now the sun killers, Kreutz sungrazers, fragments of a giant progenitor comet that shattered centuries ago. They pass within 0.01 astronomical units of the Sun, less than 2 solar radii. Perihelion temperatures reach 1,000 degrees Kelvin. Most don't survive. Since the Solar and Heliospheric Observatory launched in 1995, over 5,000 Kreutz sungrazers have been discovered. None of the small ones survived perihelion. Only the largest, nucleus diameters over 1 kilometer, have a chance. C 2024 S1 Atlas, discovered September 27, 2024, promised to be spectacular. Early projections suggested naked eye visibility, but disintegration started at 0.7 astronomical units pre-perihelion. The nucleus radius was under 600 meters. By October 26, entering the SOHO-LASCO C3 field of view, it was clear the comet wouldn't make it. It brightened from magnitude 14 to 8.1, then faded catastrophically. On October 28, perihelion day, nothing remained. Rotational instability from outgassing torques ripped it apart. Temperatures at 0.008 astronomical units, 1.73 solar radii, melted refractory grains. Olivine composition vaporized at 1,000 degrees. The comet was destroyed not by tidal forces, but by its own sublimation. The Great Comet of 1843 survived. C. 1882, R1 Out, the Great September Comet, survived and fragmented into multiple pieces visible for months. Comet Ikeiseki. In 1965 may have been one of the brightest comets in the last millennium, reaching magnitude -10, visible in daylight. Its nucleus exceeded 1 kilometer. It survived perihelion, barely and broke into 3 fragments. The Kreutz family's original progenitor likely orbited with a period of 750 years. Broke apart in the year 371 BCE, according to models by Zdeněk Sekanina. Fragments have been arriving ever since. The next major cluster may arrive in coming decades. The Great Comet of 1843 appeared in February, visible in broad daylight near the Sun. Tail stretched up to 2 astronomical units, 300 million kilometers. Observers reported it looked like a luminous sword hanging in sky. Perihelion distance 0.005, 5 astronomical units, just over 1 solar radius above surface. Temperature at that distance exceeds 2,000 degrees Celsius, rock melts, iron vaporizes, yet the nucleus survived. Ejected massive amounts of material and continued outbound. Estimates suggest nucleus diameter between 30 and 50 kilometers, one of largest Kreutz members. 39 years later, September Comet of 1882 appeared. Even brighter than 1843, magnitude -17 at peak, bright enough to cast shadows at midday. Multiple observers watched it pass solar disk with telescopes, protected by dense solar filters. Nucleus appeared star-like. Didn't resolve into disk even at closest approach, suggesting compact structure despite large mass. After perihelion, it broke into at least 4 fragments. Each fragment followed slightly different orbit. 2 fragments returned in 1965, Comet Ikeiseki and Comet Pereira. Others may return in coming centuries, or they may have disintegrated completely, contributing to smaller Kreutz population observed by SOHO. Heinrich Kreutz published his analysis in 1888, demonstrating that comets of 1843, 1880, and 1882 shared nearly identical orbits. He proposed they were fragments of single-parent body that broke up during previous perihelion passage. Modern calculations suggest the original breakup occurred during return in 371 BCE. Observed by Greek philosopher Aristotle, who wrote about bright comet appearing in winter sky, that comet was the progenitor. On its next return around 363 CE, Roman historian Ammianus Marcellinus wrote, "Comets were seen, plural, the first fragmentation, pieces returned in 1106. Great comet observed in China, Japan, and Europe. Described as gigantic, with tail stretching 100 degrees across sky. More fragments returned 1138. Then 1843, 1880, 1882, and many smaller fragments detected by SOHO since 1995. The family is still fragmenting, still spreading out along shared orbit, and will continue arriving for centuries until solar radiation and collisions erase every piece." Sun grazers aren't limited to Kreutz. The Meyer group, Krecht group, Marsden group, all families of Sun approaching comets with perihelia under 0.1 astronomical units. Each family represents a shattered parent body. Each passage near the Sun evaporates mass, changes orbits, breaks the nucleus further. Eventually, every sun grazer will evaporate completely or collide with the Sun. Their lifespans measured in thousands of years, not millions. Now the asteroid belt surprise, main belt comets, 14 confirmed as of October 2024. They orbit between Mars and Jupiter, 2.4 to 3.2 astronomical units from the Sun, where temperatures shouldn't allow ice to survive. But ice persists in subsurface pockets. Minor impacts excavate it. Solar radiation sublimates it. Tails form, 4, 5, 6, P, pan-stars, confirmed in October 2024, showed recurrent activity, proof of sublimation. Driven mass loss, not one-time impact ejecta. Main belt comets were first discovered in 2006 by Henry Shea and David Jewett. 7968. Elst Pizarro, discovered in 1979 as an asteroid, revealed a tail in 1996. It orbits every 5.6 years in the outer asteroid belt with near zero eccentricity and 1.4 degree inclination, an asteroid orbit harboring comet behavior. Activity persists for months during each perihelion passage. Ice hidden beneath dust, exposed by collisions within the last 100 to 1,000 years. The existence of main belt comets supports the hypothesis that asteroid impacts delivered Earth's water. The deuterium to hydrogen ratio in Earth's oceans is too low for classical Oort cloud comets to be the primary source. But main belt comets, formed closer to the Sun in warmer conditions, match Earth's water signature. If main belt comets bombarded early Earth 4 billion years ago, they carry the oceans you drink from today. Active asteroids complicate the picture further. They show cometary features, but aren't necessarily icy. 596. Sheila erupted in 2010. 3 dust tails formed from an impact cone and downrange plume. An impactor roughly 35 meters in diameter hit at cosmic velocity, kicked up dust, created temporary comet-like appearance. P 2013 R3. Catalina Pan-STARRS. Broke apart in 2013. 4 fragments observed moving together with shared tail. Rotational fission, not sublimation. The object spun too fast, structural integrity failed, nucleus split. Then there's NASA's Double Asteroid Redirection Test. September 26, 2022. The DART spacecraft impacted Dimorphos, the moon of asteroid 65803 Didymos, impact velocity 6.1 kilometers per second. Dimorphos lost approximately 1 million kilograms. Dust plume brightened the system. A 10,000 kilometer tail persisted for months. DART made Dimorphos an active asteroid under precisely known conditions, the first time humans created a comet-like object. Global resurfacing occurred. Impact crater several tens of meters formed. We proved asteroids can be moved. We proved kinetic impactors work, and we learned that dust production from impacts far exceeds models predicted. Near-Earth comets, 123 known as of December 2024. Short-period comets with perihelia, less than 1.3 astronomical units that can approach Earth. 6 Encke types classified as near-Earth objects. 36 Halley types, 153 Jupiter family comets. They're surveyed. Cataloged a tract. Impact probabilities calculated decades in advance. But they're not the primary threat. That title belongs to potentially hazardous comets. Potentially hazardous comets have Earth minimum orbit intersection distances less than 0.05 astronomical units, 7.5 million kilometers, or 19.5 lunar distances, and are large enough to cause regional devastation. 109P Swift-Tuttle qualifies. Nucleus diameter, 26 kilometers. Orbital period, 133 years. Next perihelion, July 2068. Its orbit brings it within 0.15 astronomical units of Earth. Not an immediate threat, but within the hazard zone. If perturbations ever shift its trajectory, Swift-Tuttle carries enough mass to trigger an extinction-level impact. Current calculations show no collision risk for thousands of years. But orbital mechanics change. Gravitational resonances change. A Jupiter flyby in the wrong place at the wrong time changes everything. In January 2025, Asteroid 2024, YR4 briefly reached Torino scale level 3, the highest rating since 99942 Apophis in 2004. Peak impact probability was 3.1%. For December 22, 2032, 55 meters diameter, if it struck, it would have been a city killer. Astronomers scrambled. James Webb Space Telescope observations scheduled. Orbit refined. By February 23rd, Torino scale dropped to 0, no threat. But for 1 month, the world had a confirmed potential impactor with visible countdown. The DART mission proved we could deflect it. Launch vehicles in 2028 had sufficient throw weight to intercept in time. But the scare was real. Currently, as of February 2025, only 21 potentially hazardous objects on NASA's Sentry Risk Table cannot be excluded as threats over the next 100 years. Over thousands of years, orbits evolve. Today's safe orbit becomes tomorrow's collision course. Of 37,378 known near-Earth objects, 37,255 are asteroids, 123 are comets. That ratio is deceptive. Comets contribute disproportionate risk because of velocity. An asteroid at 20 kilometers per second is manageable. A long-period comet at 58 kilometers per second is apocalyptic. Interstellar comets, 3 confirmed. 1 I Oumuamua, discovered October 2017. Hyperbolic trajectory, eccentricity 1.2, length 400 meters, width 40, dark red surface, non-gravitational acceleration, suggested outgassing but no coma visible. probably a nitrogen ice fragment from a Pluto-like exoplanet, though debate continues. Velocity at solar system entry, 26 kilometers per second relative to the Sun. Closest approach to Earth, 0.16 astronomical units. Gone forever within months. Pan-STARRS telescope in Hawaii detected Oumuamua on October 19, 2017. Initial trajectory suggested asteroid. Then refinements revealed hyperbolic orbit, eccentricity 1.1956. It came from direction of Vega, though Vega wasn't at that location 300,000 years ago when Oumuamua passed through that region of space. Light curve analysis showed brightness variations, suggesting rotation period 8.1 hours and elongated shape, length to width ratio 5 to 1 or higher. Spectroscopy revealed red color similar to organic rich surfaces in outer solar system, but no outgassing detected despite close solar approach. 0.255 astronomical units on September 9th. Inactive. Dead. Were composed of material with extremely high sublimation temperature. Then, non-gravitational acceleration appeared. As Oumuamua moved away from Sun, it accelerated slightly beyond what gravity alone would produce. Outgassing from comet activity causes this effect: rocket thrust from ejected gas. But no coma, no tail, no spectroscopic evidence of gas emission. Harvard astronomer Avi Loeb proposed artificial origin, light sail or probe from another civilization. Most astronomers favor natural explanations. Nitrogen ice from disrupted exo, Pluto could sublimate without producing visible coma. Or molecular hydrogen outgassing from irradiated ice, or unusual shape creating radiation pressure effects. Debate continues. Oumuamua is now over 4 astronomical units from Sun, fading beyond detection capability, and will never return. We had one chance. We missed it. Next time we'll be ready. 2, I. Borisov, discovered August 2019. Clearly cometary. Active coma, visible tail, carbon monoxide. Rich composition. Nucleus diameter under 1 kilometer. Orbital eccentricity 3.36. Velocity at entry 32 kilometers per second. It resembled solar system comets but with interstellar chemistry. Water detected. Cyanide detected. Carbon monoxide levels higher than typical. Possibly one of the most pristine comets ever observed because it never experienced close solar passes until entering our system. Observations lasted 6 months before it faded beyond detection. Crimean amateur astronomer Gennady Borisov discovered it. August 30th, 2019, using homemade 0.65 meter telescope. Follow-up observations. Revealed hyperbolic orbit. Comet designation 2. I. Borisov assigned, second interstellar object. Unlike Oumuamua, Borisov looked exactly like Comet. Coma diameter, 60,000 kilometers. Dust tail extending hundreds of thousands of kilometers. Spectroscopy detected CN, C2, OH, NH2, standard cometary molecules, but carbon monoxide to water ratio exceeded most solar system comets by factors of 3 to 9 depending on measurement date. This suggested formation in extremely cold environment, colder than Kuiper Belt, possibly scattered disk or even Oort cloud of another star system. Nucleus color was red, similar to Oumuamua and solar system comets. Confirming organic rich composition is common across stellar systems. Multiple spacecraft and ground telescopes tracked Borisov from August 2019 through March 2020. Hubble captured detailed images showing coma structure and tail morphology. ALMA telescope detected carbon monoxide emission directly. VLT in Chile measured dust properties. Altogether, over 50 scientific papers published analyzing Borisov data. Key findings? Dust grains were porous, sizes ranged from sub-micron to millimeters, dust to gas ratio around 1. Water production rate peaked at 26 kilograms per second, near perihelion. The comet was active from 4 astronomical units inbound through 3 astronomical units outbound. Then it faded. Last detection was April 2020. It's now beyond solar system's edge, traveling outward at 32 kilometers per second, headed toward constellation Telescopium. In 300,000 years it will pass near another star. Maybe that star has planets. Maybe observers there will detect Borisov arriving and wonder about its origins, just as we did. 3 I Atlas, discovered July 1, 2025. The largest interstellar visitor yet. Estimated mass 33 billion tons, 3 to 5 orders of magnitude more massive than Oumuamua or Borisov. Nucleus diameter estimates range from 440 meters to 5.6 kilometers. Velocity at entry, 58 kilometers per second relative to the Sun. Eccentricity, 6.137, extremely hyperbolic. The trajectory appears almost straight. Activity detected as early as May 7, 2025 at 6.4 astronomical units. Coma diameter grew from 13,000 kilometers in June to 26,400 by July. Reddish dust suggests D-type composition. Irradiated organics, tholins, similar to solar system comets. James Webb Space Telescope observed 3I Atlas on August 6, 2025, using the near-infrared spectrograph. Water ice detected in fine grains under 1 micrometer. Amorphous ice structure likely, though crystalline cannot be ruled out. Swift Observatory detected hydroxyl gas, chemical fingerprint of water, on July 31 and August 1. Water ice grains sublimating between 4,000 and 10,000 kilometers from nucleus, driven by carbon dioxide and carbon monoxide outgassing. Cyanide and atomic nickel vapor also detected. The nickel emission isn't unusual, seen in various comets including 2I Borisov. 3I Atlas is thought to be between 3 billion and 11 billion years old. If 11 billion Tor, it's roughly as old as the galaxy, twice Earth's age. A frozen relic from a star system that formed when the universe was 3 billion years old. It carries primordial chemistry from conditions we can barely reconstruct. And it's here, passing through, offering one chance to study alien planetary formation before it vanishes forever. Perihelion occurred October the 29, 30, 20, 25, at 1.4 astronomical units, just inside Mars' orbit, hidden behind the Sun during closest approach, reappeared mid-November, closest Earth approach, December 19, 2025, at 1.8 astronomical units. Then a Jupiter flyby, March 1620 at 26, at roughly 50 million kilometers before escaping the solar system permanently. Harvard astronomer Avi Loeb noted a major anomaly. 3I Atlas is 3 to 5 orders of magnitude more massive than previous interstellar objects. Given limited reservoir of heavy elements and stellar ejecta, we should have discovered roughly 100,000.1 kilometer scale objects like Oumuamua before finding one as large as 3I Atlas. We've only detected 2 prior interstellar visitors. Either we're statistically unlucky, or 3I Atlas represents a different population, perhaps a primordial material ejected during early galactic star formation rather than recent planetary system ejecta, extinct comets. The ghosts, they passed close to the Sun repeatedly. Lost all volatile ices, lost all dust. Now they orbit like asteroids, indistinguishable except for residual trajectory. 3D Biela split into 2 pieces in 1846, disintegrated completely by 1872. Never seen again. 5D Borson, discovered 1846, lost after 1879. Perihelion distance 0.59 astronomical units. Orbital period 5.5 years. It faded, disappeared, and searches since have found nothing. The Andromedid meteor shower may be its remains. Manx comets blur the line further. C 2014, S3, Pan stars, and 26 others, found between 2013 and 2017, orbit like long-period comets, but show no activity, no tails, no coma, rocky surfaces with minimal ice. They probably formed in the inner solar system like asteroids, but got ejected to Oort cloud distances during early planetary migration. Then, gravitational perturbations brought them back inward. Same trajectory, different composition. Scattered disk objects occasionally get kicked inward and start outgassing. Centaurs, bodies orbiting between Jupiter and Neptune, sometimes activate. 2-9P Schwassmann. Bachmann, one orbits entirely between Jupiter and Saturn, but exhibits periodic outbursts visible from Earth. Definitions break down. The Kuiper Belt, from 30 to 50 astronomical units, holds thousands of icy bodies. Pluto, Eris, Makemake, Haumea, dwarf planets large enough to reach hydrostatic equilibrium, but also millions of smaller bodies, comet nuclei waiting for perturbation. Gravitational interactions with Neptune occasionally send Kuiper Belt objects sunward. They become Jupiter family comets, Halley types, or long-period comets depending on the specifics of their ejection. The Kuiper Belt is the source of short-period comets. The Oort cloud is the source of long-period comets. And both reservoirs formed from the same primordial material, just scattered to different distances during planetary formation 4.6 billion years ago. So which comet type should terrify you? Not the periodic comets. We track them. We know their orbits. We'll see them coming. Not the main belt comets. Too small, wrong trajectories. Not the extinct comets. They're already dead. The real threats are 3. First, long-period comets from the Oort cloud. Pristine, massive, fast, unpredictable. 1 year warning at best. Impact velocity 58 kilometers per second. A 10-kilometer nucleus at that speed delivers energy equivalent to 100 million megatons, 10,000 times the entire world's nuclear arsenal. Global firestorms, impact winter lasting decades, extinction level event. Probability is low, 1 in a million per year for catastrophic impact, but the consequences are total. Second, interstellar comets. We've seen 3. Vera C. Rubin Observatory's legacy. Survey of space and time will detect dozens per year once fully operational. Most will be small, but eventually a large one arrives. Velocity could exceed 60 kilometers per second. Composition unknown. Trajectory unknown until it's already here. 0 warning time for deflection missions. If a massive interstellar comet entered on collision course, we'd watch it arrive. Nothing more. Third, perturbations we can't predict. A stellar flyby disturbs the Oort cloud. Cometary shower begins. Dozens of large comets arrive over centuries. Impact rates increase by orders of magnitude. Nemesis hypothesis, a solar companion star in long elliptical orbit, could explain periodic mass extinctions if it periodically disturbs the cloud. No evidence for Nemesis exists, but the mechanism is sound. Or a giant molecular cloud passage. 5 times 10 to the 5th solar masses at 20 parsec radius moving through the Oort cloud would gravitationally strip outer regions, send fragments inward. The cloud would take millions of years to recover. During that time, Earth would face elevated impact risk. As of October 2025, no confirmed threat exists. Every known comet with collision potential has been calculated forward thousands of years. None hit Earth. But calculations depend on knowing the comet exists. Discovery rate for near-Earth asteroids exceeds 3,000 per year, thanks to surveys like ATLAS, Pan-STARRS, Catalina Sky Survey. But long-period comets arrive unannounced. And interstellar comets arrive even faster. Detection improves. Rubin Observatory will image the entire southern sky every 3 nights beginning 2025, finding moving objects automatically. NASA's Near-Earth Object Surveyor, Infrared Space Telescope optimized for dark asteroids and comets, launches 2027. ESA's Comet Interceptor, SHIO, waiting in space until a pristine long-period comet appears. Launches 2029, then intercepts the target during close solar pass. We're building infrastructure to see what's coming. Deflection technology works. DART changed Dimorphos' orbital period by 33 minutes using pure kinetic impact. Models predicted 10 minutes. Actual result was 3 times greater because ejecta momentum transfer exceeded spacecraft momentum by a factor of 3. Hitting a comet or asteroid doesn't just move the target, it excavates material that adds thrust. With sufficient lead time, even large objects are movable. But lid time is the constraint. 10 years to prepare a deflection mission. Build the spacecraft, launch, intercept, and confirm trajectory change. That's the minimum for known threats. For long-period comets detected at 5 astronomical units, we have months, maybe a year. Not enough. For interstellar comets, detection often occurs after closest approach. Oumuamua was discovered after perihelion. We saw it leaving, not arriving. If a larger interstellar comet on collision course arrives at 60 kilometers per second, we get 1 observation window. Then impact. That's why classification matters. Periodic comets give decades warning. Long-period comets give months. Interstellar comets give none. And every type carries different composition, different fragility, different behavior under stress. Hitting a strong nucleus with kinetic impactor works. Hitting a rubble pile might shatter it into dozens of pieces, same total mass, but now multiple impactors instead of 1. Pre-mission characterization is critical. We need spectroscopy, radar, shape models, spin state, density estimates, all before launching deflection. The final nightmare scenario isn't a single impact. It's a comet that fragments in Earth's atmosphere. Shoemaker-Levy 9 hit Jupiter in July 1994. 21 fragments spread along 600,000 kilometers, sequential impacts over 6 days. Each fragment delivered megatons to hundreds of megatons depending on size. Dark impact scars in Jupiter's atmosphere persisted for months. Fragments ranged from hundreds of meters to 2 kilometers diameter. If that hit Earth, multiple impacts across continents simultaneously. No warning, no evacuation, just sequential city killers arriving in waves. Comet nuclei are fragile, low density, 0.5 grams per cubic centimeter, typical, loosely bound ice and dust. Stress from tidal forces, thermal shock, rotational acceleration, outgassing jets, all can fracture the nucleus. C 2012, S1, ISON, fragmented at perihelion. C 2024, S1, Atlas, fragmented before perihelion. 73P, Schwarzmann-Bachmann 3 split in 1995. Fragmentation is common, and if a comet fragments during Earth approach, we face multiple simultaneous impacts. Airburst over multiple cities. Tunguska events spread across continents. No shelter, no escape. Detection and characterization become survival tools. Current survey completeness for near-Earth asteroids above 1 kilometer diameter is 95%. For comets? Lower. Jupiter family comets are fairly complete. Halley types less so. Long-period comets, we only see what arrives. And dormant comets masquerading as asteroids remain invisible until they activate. In July 2025, Atlas discovered 3 I-Atlas at 17 magnitude, faint, barely visible, but caught because of automated surveys running nightly. Without Atlas, Pan-STARRS, Catalina, Zwicky Transient Facility, and upcoming Rubin Observatory. We'd miss most comets until they brighten near perihelion. By then, deflection options narrow. Early detection is the only defense. So here's the accounting. 4,584 known comets. 123 near-Earth comets, 3 interstellar visitors, 14 main belt comets hiding in asteroid belt, thousands of Kreutz sun grazers discovered since 1995, long-period comets arriving from Oort cloud, 1 trillion bodies at 50,000 astronomical units waiting for perturbation. And every comet represents leftover material from solar system formation 4.6 billion years ago, carrying frozen records of conditions that built planets. But some carry more than records. Some carry city-killing energy, some carry extinction-level mass, and some arrive without warning, traveling at speeds we can barely intercept, on trajectories we can't deflect, with compositions we don't understand. Those are the comets that should terrify you, not because they're likely, but because when one arrives, we'll have minutes to realize, hours to confirm, and zero time to stop it. That's the taxonomy of terror written in ice and dust. On January 2025, soil cores from Greenland ice sheets revealed iridium spike at 12,800 years ago, younger Dryas boundary. Comet impact hypothesis suggests fragmented comet airburst over North America, triggered rapid cooling, megafauna extinction, and Clovis culture collapse. Platinum, microspherules, nanodiamonds, melt glass, all impact markers. If confirmed, a comet fragment did this, not millions of years ago, not during dinosaur extinction 12,000 years ago, when humans already walked Earth, when civilizations already existed, and survivors had to rebuild from ashes while temperatures dropped 10 degrees Celsius within decades. That's the story comets tell, not ancient history, recent memory, frozen time bombs waiting in darkness. And somewhere in the Oort cloud, drifted at 100,000 astronomical units. The next one is already falling toward the sun.